So when we're, thank you very much, when we're looking at our activities, it's 8:09, bell work is done, and some people still don't have their notebooks open. I understand the tables are still in group table format. They'll be reformatted soon. I'm not gonna wait though. I'm gonna keep going. So that's what it's gonna be like every morning. If you can't get your act together, get here. I'll tell you, you got 2 minutes to get bell work done, and it will cost for points. Bless you. I hope the posters went well. They'll be graded by this evening, I hope. But let's move on. We're going to take a look at this one organelle known as a chloroplast. And we're going to look at different structures of this organelle. Oh, I should mention that your cell bonus quiz is no longer available for turning in, so please don't you don't need to tell me, to write me messages telling me you can't submit it, because you can't. It's we're done with the bonus. That was an offer I made to be done by this morning. Hold on a second. So when we're looking at the chloroplast, it's important that we look at the anatomy of a chloroplast and actually take a look at its structure. Does anybody know what chloroplasts do? Yeah?
They produce energy using photosynthesis.
Produce energy. By way of photosynthesis. Let's take apart that statement. Let's think about what that means. What does energy mean? You guys use it all the time, don't you? They even have drinks. It's called energy drinks. Yeah? That's all you got to say. That's perfect. It's something that's used to do work, right? Energy allows for work to be done. That's a perfect definition. Now let me unpack that a little more. What does work mean?
Get something done.
Get something done. Well, let me give you a simple formula for work. Work equals force times distance. So what does that mean? What does that tell you? If work equals force times distance, what must happen if work is going to be done? Say again? Anybody? If work equals force times distance, what has to happen? You gotta have to have force. Movement. You have to have movement. Who said that? Oh, very good. It's perfect. You have to have movement. Right? So work equals force times distance. And so that means that there has to be some kind of movement in order to do work, and energy is for work. So how does light and photosynthesis, what is photosynthesis? Kind of gave you a clue already. The word photo, what does photo mean? What does photo mean? Light. Light means light. Light used for what? What does the word synthesize mean? Or synthesis?
To make.
To make. Light to make. So this thing called the chloroplast is going to use light to make something.
Light to make energy.
Light to make energy. In what form? And does energy have more than one form?
Yeah.
What are some of the forms of energy that you know?
Sleep.
Sleep.
Food.
What part of food? Is all food energy?
Energy bars.
Okay, it's kind of, what does that mean? Proteins are energy?
Potentially good fats, kinetic.
We have a lot of ideas out here. Kinetic, I heard water, I heard proteins, potential. Well, how about these simple ones? Electricity,
Bruh.
heat. Let's see, kinetic energy, I like that one. Potential energy. Chemical energy. Of all of these, what do you think is the one we're really interested in when we're talking about chloroplast? Of course, I should have put light, and I should say light and heat energy are combined, really. Heat is a type of light, right?
What does the P stand for?
Potential energy. Yeah. And electromagnetic energy, which, of course, electricity is part of. So there's a lot of different kinds of energy, right? Which of these do you think is the one we're going to be really focused in? Two of these we're going to be focused in on.
Electricity and light.
Oh, I should mention there's some subclasses here as well. There's mechanical. You've heard of mechanical energy, right? You've heard of mechanical energy?
Mm-hmm.
Okay. Which are the two that we're really interested in when we're talking about? Yeah, chemical. Why do you think chemical? Yeah, because the chloroplast probably has some kind of chemical change going on. Excellent, excellent. And what's the other one? What's the other one we're interested in? Yeah,
Light.
light. How do you know it's light?
Because photosynthesis is light.
That's right, because photosynthesis is light. So we're making something, probably something chemical, right? And that's going to be the source of energy. Excellent. So we unpacked it. Based on what you knew, we kind of unpacked it. You probably knew most of these forms of energy, right?
Mm-hmm.
And we're able to unpack some. That's nice. Now, chloroplast, it turns out, it's important that you know this structure. So there's double membranes. This is going to be important for future discussions. It has these little stacks of membranes. They look like pancakes. Please don't put pancakes on any test that I give you. They are not pancakes. They are membranes. They look like a stack of pancakes, and when you look at them underneath the microscope, they look something similar. They're just these stacks of membranes inside the chloroplast. They're all connected to this inner membrane. Should make them all green. And we call these stacks, granum. All right, there's a stack, and these membranes themselves are called, each one of the stacks is a thylakoid.
So the group of stacks is called granum?
Mm-hmm. These are thylakoids. And these thylakoids, what they do is they create a bunch of spaces. You see there's a space here, right? They have these separations. Remember we talked about how important it is that a cell have different spaces, right? For different functions. You remember that? So these thylakoids, they have these pigments called chlorophyll. Chloroplasts have chlorophyll. I can tell you, and I'm pretty good at predicting this because repeatedly it happens, and repeatedly I warn, and repeatedly people ignore, and repeatedly people do poorly. But what's interesting is that because these words are all so similar, right? Because we have words like chloroplast and then chlorophyll, guess what people do all the time? They get them confused. So chloroplast, are the organelle. And chlorophyll is the pigment. What do pigments do?
Color.
All right, they give you color, but that's not really what they do. So we talked a little bit about this when we did paper chromatography. So
Our pigment, doesn't it like store like heat or something?
you're so close. You're so close. It's so good. Yeah, so pigments, again, you're very close to the fact that what pigments do, when you see this green pigment here, and I'm using green for a reason, right? Why am I using green? Because that's the color plants are. So pigments, what pigments do is pigments absorb what? What do they absorb? Light. And pigments are chemicals, molecules that absorb light. Not all molecules absorb light, right? At least not well. Glass, for instance, does glass absorb light very well? That silicon that makes up glass? No, it doesn't. It lets light right through, no problem. So not every molecule acts like a pigment. But so pigments absorb light, and they absorb it at a specific frequency. Now, do you remember what frequency means? Let me remind you. A wavelength of light looks something like this. We call this a photon. Have you heard of this photon? This word photon, have you heard of it before? Sorry to hear that. We measure a photon, a wavelength, from wave crest to wave crest. So that's a wavelength. The symbol we use for wavelength is lambda. Lambda is a Greek letter. So lambda is a photon. That's the wavelength of a photon. Now there's different wavelengths. So, and depending on the wavelength, you have different frequencies. So very quickly, if you can imagine a train car with car lengths of this sort, versus a train car that's much long, with train cars that are much longer. What would be the frequency if I'm sitting here and I'm looking at this spot right here, okay? How many train cars from train one, which one would allow for more train cars to pass by if they're all going at the same speed, right? So if both trains are going at 60 miles an hour, let's say, which one will have more train cars pass this blue line? Why? Because they're smaller. so they can pass by quicker. You have more, every second you have more train cars passing by for number one than you do for two because they're shorter, right? So the shorter wavelengths allow for more energy to get by every second. Does that make sense? Yes or no? I mean, does it intuitively, can you imagine it? Can you imagine that? The idea that can you imagine that concept that the smaller it is, the more frequency they come by? Yes? The more frequent they come by.
I don't understand that.
All right, what don't you understand about that?
But why does it matter if it's like smaller or bigger?
But look at it. Look at the drawing. Think about it. Think about it for a second. If they're both going the same speed, if it takes this one 1 second to get through, how many of these can come by in the same second? It looks like about 3 of them, right?
Yeah.
Right? So for every one of these, 3 of these come by. So that's why these go by faster. The more often, not faster because they're going the same speed, right? Right?
Yeah.
So at the same speed, the shorter car goes by faster than the longer car. Yes? Everyone? It's important you see that or you won't understand the next step, the next statement. So it turns out light has colors as frequencies as well, wavelengths and frequencies. So let's take a look at red. What are the colors of the rainbow? Of light? Red, orange,
Yellow.
orange, yellow, green.
White. I mean.
Blue, indigo,
That's right, blue, indigo, violet. Violet's actually a combination of colors, right?
Oh, where's purple?
It's Roy G. Biv, I heard someone say, and that's correct. ROYGBIV. Let's take a look at the first few colors here. Let's take a look at hold on a second. Let's see here, hold on a second. Let me pause. All right, so let's take a look at this. Let's see, if we say red is 620 to 780 nanometers. Nanometers is a very small measurement. We talked about that last week, right? Nanometers is a very small measurement. Actually, I made some copies, but I haven't copied enough for you, everyone. Orange is smaller than that, smaller, 585 to 620 nanometers. Yellow is 570 to 585 nanometers. And green is 490 to 570 nanometers. And blue is 440 to 490 nanometers. Indigo is 420 to 440 nanometers. And violet's about 400 to 420 nanometers. So what we can see goes all the way from 780 to 400. So anywhere from 400 to 780 are the colors that we see with our eyes. Is that clear? Every other color is a combination of these. we can see subtleties, right? So is it 620, is it 625, is it 630? So there's all, the colors that our brains interpret, they turns out to be millions of colors or whatever, is just a combination of all these different shades of these primaries. Yes?
Who got the idea to measure colors? Is my question. It's like, who came up with the idea that we should measure on how our brains can perceive color measurement-wise?
Well, we don't know how our brain, we don't look at how our brain perceives color lengthwise. What we do is we have this machine called a spectrophotometer, and it actually can measure the length. It can measure, it does a lot of, well, different ones do different things. But a spectrophotometer can actually take a look at the length, and it's, I don't really want to get into it, but you can actually measure a single band of light. Does that make sense?
Yeah.
And so by doing that, we can actually look at, we can split the color up, split it up using a prism. You've heard of prisms, right? Basically what raindrops do in the sky and allow rainbows to occur. I want to point something out. I got half the boys and girls in the room with their backs to me, giggling and laughing and everything's a joke. Why don't you guys that have your backs to me turn around and go to the other side of the table and face this way? As if I'm trying to teach you something. Let's just pretend like that's what's happening here. Yeah?
So the rainbow is a photon?
The rainbow is a splitting of light. So what happens is when you have a small raindrop, and I don't want to spend too much time with this, a raindrop water is clear, there's no color to it, but when light comes in, it goes in as what you call white light from the sun comes in. White is a combination of all the colors. Our brain can't perceive the difference between the colors when they're all together, so when they're all very closely packed together. So what our brain does is call it white. Well, the thing that you see that's white is actually all the colors banded together, bundled together. When light changes materials, all light travels at the same speed in a vacuum. But you can slow light down. You can slow light down in a vacuum, or not in a vacuum, but by changing the material it's moving through. Just as if you're punching and you're swinging a punch through the air and all of a sudden you hit water, what happens to your punch? It slows down, actually gets diverted. Have you ever tried to hit something in the water, try to go underneath? It actually gets moved. It doesn't go where you were aiming, right? So that's what happens with light. Light travels through space, and when it hits the air or when it hits water, when it changes what we call mediums. Mediums are what we call the material in which something is moving or it exists in. When white light goes from air to water, let's say, what do you think happens?
It splits.
It splits because it moves, because the faster moving stuff bends more. So the violet bends very much, and I don't know if I have a violet, but if I do, I don't know where it is. Let's just use that and hope that that's close enough to violet. Violet turns, great, that's not what I wanted. Violet turns very quickly, and so red turns not so quickly. Violet, I did it again, didn't I? I don't know why I did that. There's yellow, there's green. there's red. And there's everything in between, right? And so they split, and when they come out the other end, what you see is the lights coming from the rainbow that's produced by the splitting of light. You don't actually see the white light anymore. You see this kind of rainbow effect. In fact, my wife and I did see the violet in one of the rainbows. And this is why the sky is blue, by the way. The sky does not reflect the water. Water's not blue. Water reflects the sky. So water is when you see a blue ocean, it's actually the reflection of the sky on that water surface. Water's clear. And the sky is only blue because water in the air separates light and allows for the color separation. And of course the one that bends the most is blue, and so blue stays moving around the surface and the rest of the lights get scattered away. So
how does pollution impact the color something?
it's a great question. What happens is that there's molecules in the air act as pigments, right? Or they refract light more, right? And so by the more particulates you have, the more refraction you have, and now you start to see the oranges and the reds along the horizon because they get refracted more. Because
so if there was no pollution, it would just be blue?
It depends. There's always going to be something in the air. Volcanoes erupting, dust. There's giant sandstorms in the Middle East. They run across the Sahara. They get pushed over the Atlantic Ocean every year. So there's always something in the air. All right. So just it would be less of it, maybe less intense, maybe less of it.
How do double rainbows get there?
That's a good question. This is not a physics class, so I don't want to get too far into this rabbit hole. So let's just say this. That's how that's how light works, okay? Now, that being said, if I have this pigment, this green pigment, and this goes for any cloth, and white light's coming in, and I'm going to use this black to represent white lights coming in. What color is not being absorbed by this piece of pigment, this molecule? Say it. You think green? Why? Why do you think green? Perfect. So you have an eyeball. In order for your eye to see it, to see anything, what has to happen? Light has to do what?
Go into it.
If light goes into it, does it, by definition, light's going into it. Where in that sentence that you just stated, does it explain how your eyeball over here sees that?
Because it's reflected.
It has to be reflected. Does that make sense? That light, that color that you see has to be bounced off and hit your eye. Otherwise, forget it, you don't see it, right?
So is that what happens to people that are colorblind?
That's another story. There's this story of vision is complicated. I don't want to get too far into it because we could spend a month on it. We don't have that time. But there are pigments, there are special pigments in the back of your eye. It's called the retina. And there are different pigments back there that allow you to absorb different light frequencies and react to different light colors, right? What you call colors. And that reaction, those cells in the back of on your retina tell your brain there's something there. Let's call it green. Something there, let's call it red. And so, in fact, there's no guarantee that what you call red, I call red. Does that make sense?
Yes.
Just because you say it's red, and maybe I'm looking at the same thing and I'm calling it green. I could be looking at it and seeing something different. So that's part of the reason we do school, right? So we can all get on the same page. So people that are red-green colorblind, there are missing cells or pigments or genes. They have a gene that doesn't allow them to make that pigment, so they don't see that color. So in any case, in this case, what we see here is it's the green that gets bounced back to your eye. You're right, that's the one color among all the other colors are absorbed by this pigment except for green. Yes?
So you said whatever like color we see, that's the color that wasn't absorbed?
Exactly right. Exactly right. So the color you see is only the color that gets bounced around in the eye. That's the color that's moving from whatever you're looking at to your eyeball. Yes?
So then, what causes eye color exactly? Like, because I know there's possible to be like, have purple eyes, have pink eyes too, because it's like different forms of being albino. But what causes us to have like gray eyes, green eyes, brown eyes, and blue eyes, things like that?
You can have pink
Yes, you can have pink eyes, it's a form of albino.
Yeah. Yeah. You don't actually have a pink eye. What you have is you have no color. That's what albino means, is you don't produce any pigments. You produce no molecules that absorb light well, specifically melanin. Are you all listening? So that's why they're so white, and their skin is white, but so is their hair. They have no, so the reason their skin is pink, why is their skin pink? Why do they look pink? Yeah.
Because they lack the pigmentation.
So lacking pigmentation would be no color. Why is there color? Think. Yeah. No.
Is it because it absorbs little pigment but not
No, they make no pigment. They have a gene, there's something wrong with their genes, they produce no pigment. Their skin is white. Why is it pink? Why does it look pink to us?
I don't know.
Blood. Underneath the skin there's still blood, and blood is still red. And that's why their eyes are red. That's why anybody whose picture you take and the light gets back to their retina and bounces back out too quickly, what color do you see in those eyes? We call it what? Red eyes, right? That's because the light hit your blood vessels and bounced out before your your pupil could shrink enough to keep it in. In fact, animals tend to have bigger pupils, and so because their pupils are open wider in the dark, when you take a picture in the dark of an animal, their eyes generally are red, much redder than ours because their pupils are bigger. They open wider. In any case, this green pigment bouncing back, the color, the light bouncing back to your eye is what you call green. That's the only color that plants can't use. Right? So how can I make that statement? How do I know plants can't use green?
Because they didn't absorb it.
Because they didn't absorb it. They can only use the light energy they absorb. Okay, enough of that. Now we got to get into some biochemistry, unfortunately for you. And guess we're going to meet our favorite little friends, concentration gradients. Oh, I do love them so. Oh, my Lord. Why, oh, why? Where, oh, where has my concentration gradient been? Where, oh, where has it been? Just because I can't sing doesn't mean I won't. Boom. All right, so the making of this is really actually very cool stuff. This is like, to me, this answers so many questions. And really, what is science if it's not trying to answer questions? So, for instance, why do plants need water? Interlude. Yeah. Why do they need water to do photosynthesis? There's a formula for photosynthesis. What is it?
Water plus light equals food.
Water plus light equals food. I like that.
Don't forget CO2.
No CO2. Okay, so let's put that together. Let's put that together what you said. Water, we need H2O. Plus CO2. Okay.
Whatever that is.
Plus light, in the presence of light.
Use energy.
And we don't really put that here. And light is energy.
Use food.
We're going to change that light energy into what? into chemical form of energy. Remember? We're going to change it into chemical form of energy. We're changing the form. We're transforming the energy from light to chemical. We're going to take that light energy, we're going to put it into chemical bonds. And this is the molecule of energy across the planet. All photosynthesizing organisms make this thing. What is this? Sugar. You see why I had you memorize these things? Ah, yes. Plants make sugar. That's what plants do. Remember cellulose? Remember that whole discussion of structural versus starch versus fructose and glucose? All that. Why do you think we hit it so hard? C6H12O6. Plus what? We make sugar. Plants make sugar. Not we. We don't do this. No animal does this. Plants take CO2. Huh? They make sugar and what?
Air. Oxygen.
Oxygen, good. They release oxygen gas. Now this is a summary of the reaction. By the way, does anybody wanna take a look and tell me? Does anybody know how to balance a reaction, a chemical reaction? Yeah.
Is that a G or a Y?
Anybody else know how to balance a chemical reaction? All right, let me ask you something real quick. Even though it's not chemistry, let me ask you something. Can you create or destroy anything?
No.
So, wait, somebody said yes?
Yes.
Of course it was you. I'm kidding. We can't create or destroy. We can change things. We can change things from one form to the other. We can even, according to Einstein, we can even take energy and turn it into matter, and take matter and turn it into energy. But we can't destroy it. There's nothing we can do that we can think of to actually destroy the thing. That doesn't mean we can't burn paper, right? But what are we really doing when we burn paper? Chemically changing it to CO2 and ash, right? So that means that statement is so important. That statement is a law. A law is an observation that has yet to be proven. We have yet to collect evidence against it. So we say it's a law. Sometimes laws have slight exceptions, some exceptions, but in general laws they are not theories. Laws are things that we observe. Theories are explanations. Laws are just observations. So when we look at this law, if we think about this law, that we can't create or destroy anything. So that means that anything on this side has to be where? On the other side. The law of conservation of matter. You cannot create or destroy anything. It's a law. No exceptions have ever been found that I know of. So if we have 2 hydrogens on this side and 12 on this side, what does that mean? We got to even it out. How do we even out 12 and 2? What's the common denominator? 12 and 2? 6. 6 times 2 is 12. Is it not? Yes or no? Yes. So we put a 6 as a coefficient in front of the H2O. So now we need 6 water molecules to make 1 sugar. Does that make sense? So that's 12, that's fine, but now we have 6 oxygens plus 2 oxygens, that's 8 oxygens on this side. How many do we have on this side? 6 plus 2 is what? 8. 6 carbons and only 1 carbon. So that means the oxygen and the hydrogen are balanced, right?
Yes.
That's called balancing an equation. So now we have carbon here on this side. It's 1 carbon. Here we have 6 carbons on this side. How do we get that balanced? Yeah.
Multiply it by 6.
Multiply by 6. So get a 6 and put in front again. But wait a minute. That's 6 carbons. That's fine. But now instead of 8 oxygens, how many I have? 6 times 2 is... 6 and 2 is what? 12. Plus 6 is what? 18 oxygens on this side, right? On this, yes, 6 and 2 is 8. What do I do now?
Separate the oxygen from the carbon.
No, we can't change the molecules. The molecules are what they are. This is what we have. What do? Look at this. You do.
Divide it.
You do. We did it twice already.
Divide it.
Hey, I need you focused. What do? You have 6 carbon dioxides. That means there's 12 oxygens here, 6 here. That's 18. On this is 6 and 2. That's 8. What are you going to do?
Multiply on the other side.
Multiply on this side. I don't know. There's 6 here. If we multiply by 6, what would that do?
Even it.
That's 12 plus 2 is what? 14. 12, I'm sorry, I meant 6. 12 plus 6 is what? 18. So here's 12 plus 6 is 18. So 18 oxygens on both sides. And then to make sure we can always do what I love to do, which is do this. This is the reactants. These are products. For when we're dealing with oxygen, on this side we said we had 18, that's fine. On this side we had oxygen, we had 18. On this side hydrogen had how many? 6. No, I'm sorry, 12, right? Hydrogen on this side is what? 12. And carbon on this side was what? 6. And carbon on this side was? Everything's balanced. That's the balanced chemical reaction for photosynthesis. You have to be able to do that when you get to chemistry, so good luck on that. It's not hard. It really is pretty easy as long as you actually remember those simple rules, and you remember all you're doing is applying a law of physics. Of course, you have to actually put your mind to it, which kids always have problems with. Actually, this process is broken up into 2 steps. We have the photosystems and we have the Calvin cycle. You have the photosystems and you have the Calvin cycle. So let's be clear on this. You have 2 steps. And unfortunately for you, there's 2 photosystems, and photosystem 2 is first. Don't ask me why it's first. It is. You would ask, of course. So it turns out that we have this thing that we're going to call photosystem 2. What is this thing? What does it end up being? A protein, that's right. It's actually a bunch of little proteins in here, but it's a complex. We call it a complex when we have a bunch of proteins together to do something. Call it a complex. And it sits into the membrane of the thylakoid. The outer space of the thylakoid, the outside the thylakoid, we call that the stroma. Now this is going to be very important that you don't confuse this with stoma. Stoma is something different, but this is stroma. That's outside the thylakoid. Remember that thylakoid, those little pancakes in that space out here? That space that's out here is the stroma. And then inside the thylakoid itself is something called the lumen. The thylakoid lumen. Thylakoid lumen. All right. So this is important because what is this? This is outside and inside. This is 2 sides. So what can we have if we have 2 sides? What can we have? We can have concentration differences. And if we have concentration differences, we can have what? We can have diffusion. We can have osmosis. We can have active transport and passive transport. That's the movement we need to get work done in a cell. This is how we make things in a cell. Osmosis and diffusion. So it turns out that this thing is called Photosystem 2. And there's all kinds of little things. There's a really super cool little enzyme called P680. You don't really... I'm just gonna write it down because I think it's really cool. And P680 has this. What it does is you have. What does this represent? Do you think?
Light, electricity,
Well,
energy.
energy in the form of light, right? So light's coming in, and it's going to get captured by this thing, and it's going to release an electron. As soon as light gets in here, this pigment, chlorophyll's involved. P680 is all kinds of things that are getting involved here. But what the cool part is this is where it takes water and it breaks it off into what?
Oxygen?
Oxygen gas plus hydrogen ions. That's where oxygen is made. Right at the first step of photosynthesis, that light splits water in half. Every second, millions of these molecules are being made. But only in a specific frequency. The one frequency that it doesn't happen with is this one right here. This green frequency. It doesn't happen. That light is bounced away. Now once that happens, this electron is ripped off. Where'd that electron come from? It came from the hydrogen. All right? These hydrogens are not floating in the air or in the lumen, not in the air. But the electrons were ripped off. That electron is going to be used to pull the electron. Is going to be used to make that high energy. We're going to use that to pull the hydrogen on one side, and that's going to allow us to. It's called the electron transport chain. We're going to move it from one carrier to the next, and we're going to send that energy that is in that electron to the dark cycles, to the night cycles. We call it the Kelvin cycles. So this is photosystem 2. There's going to be a photosystem 1 as well. And once we get photosystem 2 and 1 done, we're going to send that extra energy to the Kelvin cycle, and that's where we make sugar. Not wheat, but plants and photosynthesizing bacteria. Yeah?
So this is because this is the part 2 of photosynthesis.
This is photosystem 2. That's what we call these proteins. They capture the first photon. This is one photon. Photosystem 1 is going to capture another photon.
So this process is showing photosynthesis.
This is what photosynthesis is. This is the actual mechanism. All right? All right, we'll talk more about this tomorrow. You have this protein complex called P680. It's part of a system of proteins that we call photosystem 2. Photosystem 2 is the first light. Now, this is the first step of photosynthesis. Number 1, photosystem 2 is going to take in the first photon of light, that first wavelength. It's going to absorb it, and that system is going to break an electron. It's going to take in electrons off of the hydrogens, the bonds between oxygen and hydrogen. It's going to take one of the electrons away, and it's going to leave hydrogen with an H+. Do you see it? Then two of the oxygen. Obviously, by the way, I should mention this. Obviously, if you balance it, I hope it's obvious to you, there'd be 2 hydrogen pluses. There'd be actually 4 hydrogen ions. Because look, it's 2 oxygens. But that's 2 water molecules. Do you see that? 2 water molecules come in, and then you form one molecule of oxygen, which has how many atoms of oxygen? How many atoms of oxygen? 2. So it's 2 molecules of water are going to be broken up, and it's going to take these electrons. But the point is, an electron is going to come out. There it is. Look, I'm here. I'm an electron. I'm there. There's 4 of them there now, but let's just say 1. That electron is going to get passed down a chain of carriers. It's called electron transporter chain. Electron transport chain. These proteins, they're cytochromes. They're called cytochromes. You don't need, I'm not going to test you on that. So these cytochromes are proteins that literally go from one end of, they move from one side, they pick up that electron, then they come back and move it to the other side. They move it down the line, like a game of hot potatoes. Are we clear? And actually, this is not a cytochrome. This is actually one of the quinones. Again, there's each of these proteins are just different names. I'm not caring about the name. What is it that I want you to know?
What it does.
What it does. It's just carrying. It's doing a small, quick chemical reaction. It's going to take the electron. It's going to cycle it through. It's going to take the electron. It's going to transfer it over to one of the cytochromes. This is a cytochrome here. Are you serious? It's going to take that cytochrome. That cytochrome is going to take the electron. There it is. There's the electron. It took it from the carrier, right? And then the carrier is going to go back and pick up another one. It's going to bring it on down the chain. And every time it takes an electron, all right, it's going to start pulling these hydrogen ions through. It's going to pull a hydrogen ion from this side. It's going to get pulled in by that electron. Because what is the electron going to do to the hydrogen ion? Attract it, and it's going to pull it in and pull it out to this side. So what's happening on this side?
More hydrogen is going on this side.
Hydrogen ions are accumulating over here, right? So what are you making the hydrogen ions on this side of the membrane?
Wait, what'd you say?
So this cytochrome system, this electron transport system, is pulling the hydrogen ions across the membrane. Is that right? So as the hydrogen ions come on this side, what does it become on this side of the membrane? This side becomes what? Yes, it becomes charged, positively charged, so that side's negatively charged. That's true. But what else does it become? Go ahead, think about what we've been discussing for the last month. It's accumulating hydrogen ions, so you're getting a lot of hydrogen ions over there, a lot of hydrogen ions over there. So what's it called? What is it on that side of the membrane? Perfect, yes. High concentration. So on this side of the membrane, you have high, and on this side you have what?
Low.
Low. That's powerful. That's really powerful. Because that means now you can have what? If you have a high and a low, what can you have?
Passive.
You can have diffusion, right? It's sort of like running water. It's sort of like collecting water from a river high up on a hill. What can you do with all that water? What can you do with all that water if you run it up a hill?
Osmosis.
On a hill.
Active. Up a hill active.
So if let me quickly draw it over here. Okay, so here I have this big giant pond of water. It's on a big hill. And then what can we do with this? This is a powerful this leads to a very, 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 very powerful opportunity for us. What could we do? We could dig a hole, a tunnel. I actually probably wouldn't draw it. Dig a tunnel. And then what we do with that? What are we going to do with that tunnel?
Have water. Get the water out.
Why would we want all the water out? We don't want all the water out. What do we want? We want some of it. We want to turn it. We want to connect it to a wheel, right? That's going to turn a turbine, and we're going to create. The water's going to fall, right? You have a waterfall. It's going to run down. What do we call this? Hydroelectric power. This is called the dam. Right? This is how a dam works. This is how Niagara Falls works. You got a turbine that's connected to a generator as the water flows down this tunnel, and it flows down into the river. In the case of Niagara Falls, it flows down to the St. Lawrence. It turns a turbine. It makes electricity for the entire city of Buffalo and Niagara Falls.
So they use water?
A lot of electricity, hydropower, hydroelectric power. This is very powerful. This idea of high, something being having a lot of potential energy. You can turn it into something very powerful. And your cells do it, and chloroplasts do it, and mitochondria do it. So now we have this high area over here. Now you have a low area over here. That gives us an opportunity. What are we going to do with that? We're going to do what? We're going to make a tunnel. Just like we did with the water in the lake. Is that correct? We're going to make a tunnel. This tunnel's going to be, it actually looks like this, something like it anyways. And this thing's going to turn, just like the turbine. And the hydrogen ions are going to go from where to where?
High to low.
So they're going to move from high to low. And as they move from high to low, they're going to turn this protein. As the protein turns, you go from ADP to what? ATP. Of course, you know, ADP plus a phosphate. And of course, hydrogen ions flow this way. Oh, there goes a hydrogen ion, and one after the other, just like water's flowing. Well, what's going to happen eventually is the high is going to go all the low. They're going to equilibrate, right?
Yeah.
What stops it from going to equilibrium? The tunnel's allowing it to go to equilibrium. As it goes through, we take advantage of the hydrogen ions flowing, and we collect ATP. ATP is building up. That's our energy currency for the cell. That's great. That's wonderful. That's useful. But now it's starting to get low. It's starting to go high to low. It's starting to get equal. What stops it from getting equal? Look at the system. Think about it. What stops it from getting equal? This is all along the thylakoid membrane. And don't forget, this is the stroma over here. Of the chloroplast. And this is the lumen, the thylakoid lumen. I don't know why I always put thylakoid. So here you go, inside the membrane, inside that sac, you have a high concentration of hydrogen ions. It's going to low. Man, they're going. They're going to disappear. They're going to get equal. What are you going to do? How's it stop? How's this chloroplast stopping it? Look at it. We just talked about it. I literally just told you a minute ago. It's a process. Something. If you're going to stop, guys, this is going this way. We want them to flow this way. That's why we're making them go this way so that you can make ATP. Water. Do you see water anywhere in here? Water's getting what? I'm gonna go through it. Rather than get frustrated, I'm gonna start at the beginning, and I need you to follow along. I need you to think about what's going on.
Is it active transport?
Is it that because they keep coming down?
That's right. That's right. You got it. That's what I'm trying to get. You see why I'm getting like, what? Are you guys following? So water is getting broken down. Hydrogen ions are building up. So every time water gets broken down, what happens? What do we get? Hydrogen ions. The electron gets taken, passed along. What's the electron doing? What's it doing? Attracting hydrogen ions to this side. So what is this whole thing doing? What's this energy from light doing? It's collecting the hydrogen ions, right? It's dragging them out from this side over to this side. It's making new ones by breaking up water. Do you agree that that's what's happening? All right, so this is how we build the concentration gradient. We build it here. We use the concentration gradient over here. I mean life, right? Chloroplasts do this. Plants do this. Plants build the hydrogen ion concentration over here. You're about to get a detention.
What?
You don't think I see you and Eric fooling around in the middle class? So the buildup, you're building up hydrogen ions over here, and you're using them up over here in order to do what? To make what?
ATP.
ATP. So hydrogen ions get transported. So as hydrogen ions flow back the other way and make ATP, you start to lose that concentration gradient. But what allows it not to be lost? What builds it back up again? Yeah?
The photosystem too.
That's right. Excellent. The photosystem too. Light, water, pulling in hydrogen ions. This keeps building, building, building. Even though we're using it here, we'll keep building it on this time. As long as you have what? Light and light and water. That's why plants need light and water. It builds up the hydrogen ion. It builds up the charge, right? It builds up the high, which allows us to use that to make ATP. That's the source of energy here. This is going from low to high. So what is this? Active or passive? Active transport. This is going from high to low. So it's passive. So you're coupling these reactions, right? We're putting them together. So I think it's a really excellent opportunity to learn something, to use what you have learned. You have this light reaction. I don't care that you know that this is PS or P680 and that this is I need you to know that this is photosystem 2 though. That the electrons are being carried across. That's important. The hydrogen ions are being pulled into this side to make a high and a low, to make a concentration gradient. That light is used to break up water. All right? I need you to know that the source of energy here is light, and the electrons are being used to pull the hydrogen ions, and water is broken up at photosynthesis. The very first step. That's the only reason plants need, one of the only reasons plants need, let me rephrase it, is the only reason plants need water for photosynthesis, right there. So, okay, so you use up, it goes on, the electrons. What are you going to do with those electrons? Well, you're not going to waste them. They're sitting there. And what we're going to do is we're going to transfer them over to this other protein. We're going to transfer them over to another protein that's called photosystem, another complex of proteins called photosystem, what? What do you think it's going to be called?
1.
Photosystem 1, that's correct. I know it doesn't make sense, guys. I know it does not make sense that to you that photosystem 2 comes before, at least I hope it does not make sense to you that photosystem 2 comes before photosystem 1. Correct?
Correct.
It's like you could count backwards.
All right, so we have photosystem 1, again coming after photosystem 2. We have this electron, it's low energy now, all its energy's been used up. How do you get the energy back into this electron?
Does it go back? Does that cytodrome thing come get it?
You gotta get, how do you get the energy back in there? You need a form of energy. Energy gives you energy. What are you gonna do? Where are you gonna get the energy to bring that electron back up so you can use it? It's sitting there. Hydrogen ions energy, the concentration gradient with the hydrogen ions being used to make ATP, so that's important. That's being made. But now, how do we get the energy into this electron? It's not a bad guess though, but no, that's not it. It's called photosystem 1. Photosystem 1. Here's a hint. It's called photosystem 1. Light.
I just said light. I said light.
Did you? I hate the fact that people keep saying that to me.
What?
Mitochondria is a powerhouse of the cell. Nobody really thinks about what it means.
It makes energy.
blah, blah, blah. That's all I hear. All I hear is blah, blah, blah. Think about what you're saying. So light is going to come in, and it's going to excite the electron again. It's going to that electron's going to be carried off. There it goes. Bye. I got high energy. I'm moving on. It gets transferred over. Do I need you to know what they are? No. They're just carriers. There's a bunch of electron carriers. But there is one important electron carrier you need to know. It's called NADP. That's it. It's going to pick up,
That's the energy carrier.
along with one of these H's. It's going to add a hydrogen. Let me put this all in red. These two are going to get to come together and form NADPH using that high energy electron. Okay, so now NADPH, this is your carrier. This is what you need to know. What is it you need to know out of all this? You need to know there's two photosystems, photosystem 2 and photosystem 1. You need to know that if photosystem 2 uses light and water to get the electrons to move hydrogen ions and create a high-low concentration. You need to know this protein, this enzyme, is actually an enzyme as well as an integral membrane protein. It's called ATP Synthase. You have to know that this enzyme is making ATP using the hydrogen ion concentration. You're going to see this exact same process in mitochondria. This is how energy is made. This is how you function. How all life on this planet functions. If it's a cell, it uses something like this to produce energy. It's a eukaryote anyways. Are we clear? So that's photosystem 2. Electron gets transported. In photosystem 1, again, photosystem 2, the hydrogen ion concentration is being used to make ATP. So here in photosystem 1, you're going to use that electron, transfer it over to what carrier?
NADP.
NADP to make NADPH. That has high energy. There's still a lot of energy left in there. So how many photons did we use? 2. One for photosystem 2, one for photosystem 1. We're using the electrons that we took off water, the hydrogens that we took off water. Oxygen gas is gone. We don't need it in this chloroplast. Chloroplast does not need oxygen in this case. It's just making sugar. The plant will use that oxygen. It will use oxygen. The plant can use oxygen. Where is it going to use oxygen? Anybody know? It's going to use it in the mitochondria, in the powerhouse of the cell. All right, all of this that we just looked at is happening inside the thylakoid membrane. In the thylakoid membrane of the chloroplast. It's in one of the stacks. It's in the space. Are we clear? That's all happening inside the chloroplast.
So it's happening in each one of those little...
And all over the place. This is multiplied times 1,000,000 inside each chloroplast, and there's hundreds of chloroplasts, thousands of chloroplasts in a cell, in a plant cell. Yeah.
Can you summarize the PS one more time?
I'm about to. Good question. Excellent. So that's how you see how she just thought about that? She thought about the process. She answered. She involved herself. She thought about what was going on. She's focused. She's not playing around with Eric across the room. She's really focused. Then she's like, okay, let's summarize this. Give me the bullet point. All right? That's how you have to think. All right, so let's take a look at the bullet point. We have two things going on here. You have photosystem 2, and what did we use? We used
Water and light.
that's right, water, excellent, and light in photosystem 2. And what did we and also we use what did we use water for? We got hydrogen ions, right? And electrons. And what did we get rid of? oxygen gas. That's the first step. That's one. And the second part of the photosystem 2, what did we do? The electron got transported. Just move down the membrane. Oh my God, it's time to go. All right, so you have to get out of here. Goodbye.
Oh my God.
I'm gonna go on. Get. Electron is transported down the electron transport chain. That's important. But that electron being transported allowed the hydrogen ions to concentrate, right, on one side. This transporting of electrons allows for hydrogen ions to become high on one side and low on the other. That's a concentration gradient. Do you remember that? That's what drives it. And that also, because of that, what does that do? Oops. That goes here. This is just to remind you, by the way, just in case you didn't get it the first time. This is just to remind you that this is all happening in the thylakoids. Do you see the thylakoids in the granum?
Yeah.
There's millions of these, or thousands of these apparati throughout the membranes. And there's stacks and stacks of these. And there's many, many chloroplasts in each leaf. So this has happened all, like crazy amount of ATPs being made. Crazy amount of electrons, water, light coming in and being captured. All that's happening all at once. So that the electron being transported allows for hydrogen ions to be high and allows a concentration gradient, which allows ATP synthetase to do what? Uses what? What does ATP synthetase use? The hydrogen ion concentration to make ATP. Right? That's where ATP synthetase. Synthetase means what? To synthesize, to make. It's the ATP maker. All right? So it uses the hydrogen ion concentration as it goes from high to low. It turns the machine and ATP is made over and over and over and over again.
So the ATP synthase would be like the tunnel?
This is the tunnel. That's right. Let's go back for a second. Let's zoom in. There it is. See, ATP synthetase. That's what it is. It's the tunnel that turns, that makes ATP over and over and over again. Does that make sense? It's all in the book as well, so when you read the chapter and you do the problems, you'll see it there again. But I want to make sure I explain it before you go try to read the book. That's why I like giving you the book reading after we explain it. So ATP synthetase uses hydrogen ion concentration to make ATP. So that's another part of the photosystem that's happening here at this part of. So, and ultimately, what's the last step is that's just for photosynthesis, photosystem 2. No sugar's made, right? At least not yet. No sugar made yet. Now, photosystem 1 takes what? What does photosystem 1 use? It uses,
Electrons.
that's right, the electrons from photosystem 2, right? It originally came from water, right? And it uses the electrons from photosystem 1 plus what? Light, a photon of light, to excite the electron, to give it energy. So it has the ability to do work. And then it gets what? What happens to that electron? It gets transported. Excellent. It goes to what's called an electron transporters. Do we need to know the names of the electron transporters? Quinone, the quinones and the cytochromes. Do we need to know those names?
No.
There's all kinds of quinones in cytochrome C, inside all this. No, we don't need to know it. Not for this class, not for this test. So electron transporters, what do? They just carry these things. Electron carriers, in other words, a carrier. You might see that in the book as well, carrier. Electron transporters or electron carriers. They just move the electron down the chain until it gets to the final electron transporter, which is the final acceptor, is what? The final electron acceptor is what? Who knows?
Would it be ATP?
No, ATP was made over here. There it is over here. But good guess. What's the last thing to take the electron? That's right, somebody wrote it down. NADP plus. Takes the electron and becomes what? That's right. NADPH. And that's photosystem, that's it. Those are what we call the light reactions. Why do we call them the light reactions?
Because they use light.
Because they use light. Excellent. Not difficult, right? Of course, it's very complicated. There's a lot of different steps. There's molecules that we're not mentioning. There's all kinds of chemical processes, and we can start talking about energy and all. I mean, there's just all kinds of crazy things. But this is really the simplest and the basis of the process. And it's the process that you need to understand. So now let's go through. Let's go ahead and put in yellow. You know what? Why don't we use red for the things that we've used up? Okay, what have we used? We've used water and light. We used light here, right? Okay. And what did we make? We made oxygen, right? What else did we make? ATP. Oh, we should also, don't forget that what we did is we took ADP here plus phosphate to make ATP. Don't forget that that's how we made ADP. So we actually used up some ADP as well, right? We used up ADP and phosphate. So we need to get that back somehow, or we're going to run out, right? We need to get water out somehow, or we're going to run out. We need to get light somehow, or we're going to run out, right? So these are the ways we're going to run out. These are our limiting reagents, right? But we did make ATP, so that's good. What else did we make? We used up, what else did we use up? We used up NADP plus, right? And we got NADPH. So again, is a summary of the summary of the summary. As we reduce down to the very essence of this, we took water and we took light, using all these proteins and these membranes and the hydrogen ion concentrations and the hydrogen ions and etc. And we made what? NADPH. This is not a chemical reaction. This is just a summary, right? We made NADPH and ATP. Is that correct? Do you agree with that? All right. Do you see any sugar being made here? What the heck? Where the... So this is all happening where? Where's all this happening?
In the cell membrane.
In the cell membrane, in the chloroplast, right? In the thylakoid membranes of the chloroplast. Very good, very good. So, does anybody have any idea of where the Calvin cycle? Oh, I gave it away. Dang it! It's called the Calvin cycle. Can anybody imagine where it happens? Where does it happen?
Right before the PS.
What do you think the Calvin cycle does? Think about context.
You said it's called what?
The Calvin cycle. So here's this, let's go ahead and draw this again. Here's this thylakoid, right? Let me draw it in black. Here's a stalactoid. Over here is this machinery, PS1, and PS2. Oh my God, it's time to go. I'm sorry, I've lost track of time. All right, get out of here. Now we talk about where is all this ATP, and NADPH going. So we made this NADPH. We made this ATP. Why? What's it for? What was the purpose of photosynthesis? What does photosynthesis make? Yeah. Sugar. It makes sugar. So far in this list of products, we have not made any sugar. Oh, man. And this is all requiring light, isn't it? So what? Thank you. So what are we doing? What's going to happen? What do we have to do? We have to do something. So it turns out that, remember, let me go ahead and fast forward then another slide. And we call those the light reactions, or the right, the reactions that require light, right? These are called the light independent reactions. They used to be called the dark reactions, but the problem is that they don't only happen in the dark. They happen during the day as well, but they don't require light, so they're light independent. The person who discovered it was this man named Calvin, a chemist, who discovered the cycle. I believe he's a biochemist. So, if you remember, does somebody remember the balanced equation for photosynthesis? I'm glad you have it in your notes, but let's think about this for a second. The Calvin cycle, or photosynthesis, uses, we said this earlier yesterday, uses CO2 as its source of carbon. Ultimately, it's going to make a 3-carbon sugar. That's what the Calvin cycle is going to do. So my question to you is, how many of these CO2s is it going to need? Let's balance it. How many CO2s does the Calvin cycle need? 3. That's correct. So you need 3 because you need 3 carbons to make a sugar. Does that make sense? All right. Yeah.
So in this passage that you gave us, the equation got 6 CO2 plus 6 H2O.
That's wonderful. Let's do that. Let's write the whole equation out.
Right, but why do the one you tell us right now don't have 6?
Right. No, it's the perfect question. And I love that you asked that question. So let's write down that equation. Go ahead and say it. Well, the one we figured out yesterday, the one we balanced.
H2O.
How many H2Os? The balanced equation. Who knows the balanced equation?
I do.
Yeah.
6 H2O,
Yeah.
and then little x
Plus.
CO2, 6 CO2.
And this is the L for water, but go ahead.
Equals light, or arrow, light.
Yields, the arrow means yields, in the presence of light. And we know we need 2 photons of light, right? Because there's 2 photosystems, we understand that. Actually, we'll need 4, because you'll see why in a minute. Actually, more than that. It's just to need a lot of light. All right. This is not a one-to-one relationship. All right, go ahead.
C6H12O.
C6H12O6. How many of these?
5.
5 of these?
Yeah.
Let's wait on that. Go ahead.
Plus 6O2. And the little G.
All right. And you said 5 of these. Is that right? So according to this, I have 6 carbons and here I have 30 carbons.
Oh, wait, no, my bad.
So what's the problem? What do I do, man? Somebody have the balanced equation? I don't know what to do. You should have in your notes, we wrote it down. Help, oh help.
I think that is the balanced equation.
Is it balanced now? Is it balanced the way it is?
Yes.
Yeah.
There is a 5, but it's after the. Okay, so it's.
So that is not a 5, and what that was supposed to be is a solid S. It's an S.
I'm sorry.
But it should actually be, and it's actually should be aqueous, so it should be this aqueous really is what it should be because it will be in solution. But whatever. Are we good with this then? That's the balanced equation. The question that was asked is, wait a minute, you're telling me that this Calvin cycle produces 3 carbon sugars. But the equation you gave me for photosynthesis produced C6H12O6. So it needs 6 carbons, not 3, right? Is that your question? Did I state it correctly?
Yeah.
All right. So what do you think the answer is? What's the answer? Why is it when we're talking about the Calvin cycle?
Is half.
That's right. This is producing, the Calvin cycle produces half the glucose molecule. So if you run the Calvin cycle twice, then you produce 2 3-carbon sugars. And what do you do with those 2 3-carbon sugars? You put them together to make 1 glucose. So take 2 3-carbon sugars and put them together, you get 1 of these. Does that make sense? All right, that's all that's happening. It's a good question.
What's the point of splitting it?
It didn't split it, you're making it. But you can only make them 3 carbon sugars at a time, 1 3-carbon sugar at a time. So if all you can do is make 1 3-carbon, if that's all you can do, well, it's easy to just add 2 of them together and make a 6-carbon sugar, right? It's just a chain of carbons. Am I not making sense to you?
Yeah, you make
All right.
No,
All right.
we have to now one more time.
So this Calvin cycle is going to produce this a 3-carbon sugar. That 3 carbon, it's going to have 3 carbons. I'm not going to put the rest of the stuff on there. So it's going to produce 2 of them, because that's all the Calvin cycle can do is produce 3-carbon sugars. What can you do with that if you want to make glucose?
Put it together
Put them together.
to make, yeah, you already said to
That's it. Now you got a 6-carbon sugar, and we call that glucose. Done. Isn't that easy? That's the easiest way that life has decided to do this. For whatever reason, and we can get it, I don't even know if I understand the biochemistry of it, glucose has been favored in evolution rather than this 3-carbon sugar. Is that fair?
No,
Who said no? Yeah, what's the question?
no, I said,
Oh, okay. I didn't hear it. I mean, it's okay to say no, I just don't understand. Yeah.
So like, if the photosynthesis was sped up, it would create more carbons, which would create more sugar.
That's right. You just keep it, as it keeps going, it'll keep going as long as there's light and water, right? It'll keep producing the ATP, keep producing an ADPH, and that will all go to the Calvin cycle. And in the Calvin cycle, just keep producing these 3-carbon sugars as long as you have CO2, because that's the other thing you need. You need CO2. You need carbon dioxide. So remember, it's going to use up carbon dioxide. So actually, you need 3 molecules of CO2, 3 of them, right? And that's a G for gas, it's not a 5. And those 3 carbons are going to enter the cycle. There's this enzyme. What a wonderful enzyme. Probably the most important enzyme, and someone's going to argue something about this, but I'm going to say it. The most important enzyme on the entire planet. The reason life exists as you know it, probably 2 or 3 reasons. 1, water, liquid water, probably the most important stuff on the whole planet. And the second thing is probably the most important enzyme on the planet, Rubisco. Rubisco is the enzyme that changed the world.
how you spell it?
R-U-B-I-S-C-O.
You just know it as Rubisco. I'm saving you from needing to know anything else. Rubisco captures the CO2. It does something called, and I'm going to put it down because they might use it in other places. It's called fixation. It's fixing. It's attaching. It's capturing the CO2 in the air. In a leaf, in a chloroplast, in a leaf, the leaf is sitting there. CO2 passes by, and this enzyme captures it and fixes it, attaches it to something. I'm not going to tell you what that thing is. You want to learn about it, you can. We can sit here and we can draw the carbons. We can look at where the carbons move. I don't think that's necessary. But it attaches it to an intermediate that's part of the cycle. So that's fixed. So stage 1 of this process is just fixation. There's all kinds of things that have to happen during stage 1, during fixing, in order to have the carbon attach to where the way it's supposed to attach. Then the next thing you have to do to one of these intermediates, and that's stage 2, you need to reduce this. You need to add electrons to it. Well, how are you going to add electrons to it? The only way, one way to do it, one way to reduce it, or rather to fix it, I'm sorry, I'm skipping a step. In order to fix it, to finish fixing it, it needs ATP. It actually needs 6 ATPs for these 3, 2 apiece. And you produce 6 ADP. And then in stage 2, you're going to reduce it. Reduction means you're adding electrons to it. What are you going to use how are you going to get electrons here? NADPH, that's right. The carrier, NADPH. NADPH is going to come and deliver the electrons. It's going to become NADP plus again. All right, so that's the reduction. And then it's going to go on to stage 3, where it's going to start remaking the intermediates. Here is your 3-carbon sugar. Here's your 3-carbon sugar. And you're going to do this twice. If you turn this wheel twice, you produce 2 3-carbon sugars. You can then put them together and make. By the way, you don't have to make the 6-carbon sugar. You can make other things with this, but that's just one of the things you can make. And then you have to regenerate. Stage 3, you're regenerating RUBP, and that's just one of those intermediates. And of course, unfortunately, one more thing you have to know is here, actually, interestingly, you make ATP. So how many ATPs did you need if you net? You needed 6 over here, right? But you made 3 over here, so you only really need 3 altogether because you'll remake them. This part here allows you to remake Rubisco and keep it going. Does that make sense? That's all you need to know for the Calvin cycle. This happens, by the way, in the mitochondria, not in the in the chloroplast, not in the membrane. Is that clear?
Wait, is that because it don't need light?
It does not need light. That's right. It's happening. This is happening outside the stacks. It's happening in the stroma. All right. So this is in the stroma. So where is this NADP going? It's going back to the light reactions. It's going to be recycled. We don't want it. And where's this ADP going? It's going back to the light reactions. So it can be recycled again. And away, round and round it goes. All right, have a good one. Remember to get your work turned in, please. Turn it in, resubmit, whatever you got to do. Come in for tutoring if you need it. Make sure you get this stuff memorized. Read chapter 7.
Have a pass.
Yeah.
Third period.
Yeah, give me a sec. Let me group this all together. So to summarize what's going on, we can draw a chloroplast, right? Everybody okay with that? All right. So you know that there's stacks, and by the way, in that electron micrograph, they look like little slits, and we'll look at it tomorrow. But you have the stacks, and what are these stacks called? Granum, and each individual one is called a thylakoid. That's right. And in here you have two things going on. You have photosystem 2, right? Let me zoom in. In here you have photosystem 2, right? And then you have right over here you have photosystem 1. Right in the membrane. You agree? Mm-hmm. And you have and of course you have your ATP synthase. That's going across the membrane, and what's it doing? Creating ATP over and over again. Very good. ATP from ADP and phosphate. And of course hydrogen's going out this way, so you got hydrogen ions are going out that way. Of course they're coming in this way, right? This is using what? Light. And there's light going in here too. All right, so that was simple. I hear people get it. I hear people saying the words. I'm hoping you get that. Everybody okay with that? Is that hard for anyone? If it's hard, say it now. You can rewind this video and look at it. So in PS2, we're producing something. We're taking the electron. Remember, the electron's getting transferred from one carrier to the next. And ultimately, what comes out of this thing, what goes in, is NADP plus a hydrogen ion is going in. What comes out? NADPH. So I'm going to circle these. I'm going to circle them in a different color. Let me use purple. I think this is purple. So NADPH is coming out. That's what's being produced. ATP is being produced. Do you see that? Yes? Yeah. This is all from the light-dependent reactions. So the red ones, I'm going to circle the red ones. What's being used? NADPH, NADP+. We are using some hydrogens, which we made from breaking up water. Water's used too. I should write that in here, right? And light's already put in there. And when we do water, we got oxygen, O2 gas coming out. The hydrogen ions are being used there. So oxygen is also being produced. You see that? I'm circling that one because that's being produced. It's not being used. So there it is. I'm circling it. Do you see me circling it? The red ones, we're using water. You see the red is being circled, right? So the red ones we're using, and we're producing the purple ones. Everybody good with that? Yes. This is all the light-dependent reactions, because people are saying it's hard. I need to know where. So these are the light-dependent reactions. Where are they happening? You have to know where they're happening. They're happening where?
Inside the thylakoid.
In the thylakoid membranes. Excellent. Oh, Glover. Amazing. That's right. In the thylakoid membranes. That's right. Now, this is known as the stroma. Stroma. And in the stroma, we have what? The Calvin cycle. This is where we're going to use the stuff that the light reactions made to make the sugar. What's the big enzyme, the most important enzyme, blah, blah, blah. What is the important enzyme that I just introduced you to? Rubisco. All right, Rubisco. What does Rubisco do?
Enzyme that captures it.
It captures CO2, fixes CO2. And of course we need 3 of these, right? 3 CO2s come in, they get fixed, they go through a cycle. We're using some ATP, right? We're gonna actually use 6 ATPs. So they make 6 ADPs. And my question was, where is that ADP going? That's right, it goes back. It goes back because ADP is being used. I didn't circle that. I should have circled it. ADP is being used. So this ADP, I'm sorry, that was wrong. This ADP is going back here, and it's going to pick up a phosphate, right? Pick up the energy from the hydrogen ion concentration difference from ATP synthase. It's going to pick up another phosphate and come back to be used, right? So I'll draw a purple line because that's where this is going. Do you see that? Do you see that or not?
Mm-hmm.
Okay. So they're going back. That's why we call it a cycle. They just keep going. They keep exchanging. So then the next thing that needs to happen is the second stage of the Calvin cycle, which is the reduction phase. So that was stage. This is actually it'll be the third stage. Second stage. Stage 1 was the fixing. So it fixed CO2. Stage 2 is the reduction phase. Bless you. Rather than drawing all these arrows, you know what I'll do? I'll just put little asterisks. What do you think? Will that make it easier to see? This might make sense now, but as you saw from today's quiz and from the reaction that I heard, I can tell that some people are going to be upset if they don't put this to practice. So you're reducing. What do you need to use to reduce? You need electrons. So what is it that provides electrons in photosynthesis? NADPH. Where'd that NADPH come from? NADP plus, but where'd it come from? It came from here, right? From the light reactions. That's where this is coming from. I put pH again without NAD. I hate when I do that. NADPH comes from the light reactions. And that NADPH gets turned into what? NADP plus, which ends up going where? Back here to their light reactions. Back and forth they go. Then out comes what? Sugar, a 3-carbon sugar. And then we regenerate Rubisco and RUBP, not Rubisco, but...
Is the sugar part of the third stage or still the second?
You can call it third stage if you want. And then the last stage is we reform some of our reagents and we get some ATP back. We get 3 ATPs back. So it looks complicated, but if you think about it, you break it down, it's actually not that hard. That's how the plants make sugar. That's photosynthesis. 2 different sets: light dependent reactions, light independent. Did that help?
Yeah, so the Calvin cycle is independent and
That's right. It's time to go. Please leave if you want. That's right. The light independent is independent. The light dependent is dependent. Get that work done or you will not be passing this class. Please turn in that work look at the work that I've made comments. Some of you have turned in the wrong assignment in the wrong slot. I've done all I can do for you. If you don't do your work, you don't get graded. Can I see Kaylee, and I need to see somebody else, I said. Kaylee and someone else. I told you. Scott. I need to see Scott as well. So that being said, that these NADP plus cycles over to the light reactions, the NADPH comes over here to the Calvin cycle, bringing the electrons. ADP and phosphate go over back to the light reactions, and ATP comes back over to the Calvin cycle. They share that, and they keep cycling. The only thing you really need from the outside the chloroplast is water and light, right? Once you have the chloroplast, the only thing you really need, except maybe to replenish some of the stuff you might lose by accident, is light and water. Does that make sense? So at a very, very basic level, only light and water are required for photosynthesis to go on. Now, if you flip to in your workbook, past photosynthesis, and by the way, if you look in your workbook as you're flipping through and you're looking at the Cornell notes outline on, do you have your workbooks?
Yeah.
Okay. You look at phase 2, the Calvin cycle says light dependent, light independent, and you got both, right? You have the pathway. That's what we just talked about. We talked about the light and the dark and the light independent, light dependent reactions. Then you have many kinds of chlorophyll, which I found really interesting. You should read it. I'm going to do a lab. I'm going to go to the florist and get some leaves. I wanted to do it in the spring, in the fall, but we didn't get a chance. I'll get some leaves, and we'll look at the different kinds of chlorophyll on paper chromatography. So I think it'll be fun to do. But if you look on page 92, there's something else going on. So this is happening all in the presence of sunlight. And hopefully everyone remembers from yesterday's quiz that this is a chloroplast. I can't remember, did anybody have a chloroplast question on their exam? On their multiple choice exam? You did? All right. But on the quiz there was certainly that question, chloroplast versus chlorophyll. And they show you, they draw it a little differently and a lot neater on page 92, which I appreciate. So this is a chloroplast. Where is the chloroplast found?
In the
In a plant cell,
yeah, the plant
right? And there's a cell wall, right? And then we have a cell membrane inside the cell wall. Yes? So, I don't know. I don't know. So chloroplast, the sunlight is coming into the plant cell. So sunlight's coming into the plant cell. It's hitting the light dependent, and then the light dependent reactions feed the light independent reactions what they need. The light independent reactions make the sugar, right? And then builds the cell wall, right? It then feeds the cell its energy. But sugar itself needs to be changed into what? What does a cell need? What's the cell need? Energy. In what form? And chemical energy, good. What, specifically what form? What's the currency of the cell, of all cells? ATP. The cells need ATP. So far we made a little bit of ATP in here, in the light independent reactions. There's some in here made, but not really enough to run the whole cell. Just enough to make sugar. The cell needs sugar for two things. For structure, right? We learned that. Sugar can be used for structure, in this case cellulose. That's the cell wall. And other structural components as well. And sugar can be used for energy. And so now we're going to focus on the use of sugar for energy. So now let's talk about what comes out of this chloroplast. What gets put out? What leaves? What does the chloroplast not use? Oxygen gas. That's the main one. It's a byproduct. The reason it's a byproduct of photosynthesis is that photosynthesis doesn't need it. However, this is where it gets lost, and a lot of people come to high school with a misunderstanding. And I would venture to say that most humans out there, most adults, don't understand this. Plants do use oxygen. They have mitochondria. The plant uses oxygen. The chloroplast does not, right? It's a byproduct, it kicks it out, doesn't need it. But the plant does need oxygen.
How do we get on it?
Because you answer that. So why does the plant, if the plant needs oxygen, why does it why is it producing, why do we say they're producing oxygen for us? Yeah.
Because they don't need all of the oxygen, so let's get rid of it.
Exactly. They have excess oxygen. They make too much of it. Good. So that's it. That's the trick. Is they make so much of it they don't use all they need, and it comes out of their leaves. Okay. So that's the oxygen. Going into the cell is what? What is it? Into the chloroplast? What does the chloroplast need? It needs what? It needs light. That's correct. And it needs water. So the light comes from where?
The sun.
From the sun. And we know, I'm going to draw up two of them because you need two for the light reactions, right? One for photosystem 2, one for photosystem 1. What else does the chloroplast need? What else has to go into the chloroplast? We got light, we got water going in. What else? Carbon dioxide. It needs CO2. And what captures the CO2?
Rubisco.
Rubisco. So CO2 gets in, gets captured by Rubisco, and gets used up by light-independent reactions. Now, what else comes out of the chloroplast? The glucose, I heard someone say, and that's correct. Glucose comes out. Now, interesting. There are, in the study guide that I gave you, and I want you to go ahead and do it, and go through all the trouble. And by the way, if you go to Extending Our Senses, Chapter 7 there's a little bit of Chapter 7. Am I looking at the right one? Yeah. It says Chapter 7, Cellular Structure and Function. In this packet, it says Analysis, Real-World Biology, Analysis, Extending Our Senses. You have Van Leeuwenhoek's microscope. Make sure you take a look at that because that was some extra credit stuff that I had given you on the exam. For some of you, not both versions, one of the versions had an extra credited question. Then you see that there's a comparison of photosynthesis and respiration. I would really take advantage of looking in at this as your guide to what the exam is going to look like on Tuesday, okay? So if it's on here, it's likely you'll see it, okay? So you see the different kinds of chloroplasts. I wouldn't worry too much about.
I got a question.
Yeah.
Is it gonna be, well, if it is microscope, like stuff on there, what type of microscope? Because since it's different ones to study.
You should know what a microscope is. If it's in the book, it's tested. So now let's quickly, before we get into respiration, which is going to be in mitochondria, let's go ahead and draw mitochondria real quick and then talk about some other things that have to happen. So here's a mitochondria. In plants and algae, you'll find that mitochondria and chloroplasts work together, like two wheels on a bicycle. As glucose comes out, glucose gets broken down immediately. Now, the book will walk you through. This is a very traditional way of doing this. It's going to break down where all the energy is, where all the enzymes are. When you take AP biology, you'll have to know all the enzymes, all the control points, what's called allosteric control of the enzymes. You'll have to know all that. In this course, you don't need to know that. Is that clear? You need to understand, though, in general, what's happening with glycolysis, the Krebs cycle, and then the electron transport chain. The electron transport chain is going to be it's going to seem like it's an old friend, because we just got done covering it here, really. It turns out the mitochondria does a very similar thing. So glucose comes out and goes into something called glycolysis. And glycolysis is just breaking the glucose down, and there you form a little bit of ATP. A little ATP comes out. And then the other thing that comes out is a really big one. You squeeze some energy out of the sugar, but then you make this thing called pyruvate. And pyruvate is one of those important molecules you need to know. You know, like Rubisco, you need to know that name. You need to know glucose. You need to know chlorophyll. Well, you need to know pyruvate as well. You form two pyruvates. They're 3 carbons each. And pyruvate goes into the mitochondria. So you get a little bit, by doing glycolysis, you get a little bit of ATP. You do, and we'll talk about exactly how many soon. You produce 2 pyruvates, so that still leaves you with some energy left. It goes into the mitochondria, where it automatically goes through what's called the Krebs cycle. Very much like the Calvin cycle, except it's a different cycle, obviously. Also known as the TCA cycle. The citric tricarboxylic acid cycle, also known as 3 AKAs, the citric acid cycle. So there's 3 names. I give you all 3 names because I don't know whatever standardized exam you take, I don't know which one they're going to use. So you should be familiar with all 3. That's the first step that happens to that pyruvate when it goes in there. Immediately, or almost immediately, what happens to those carbons, those 2 pyruvates, is almost immediately they get turned back into CO2. So CO2 is put out. And so, by the way, this happens in your mitochondria as well. This is what happens in all mitochondria. So that's why what do you breathe out? CO2. This is why you breathe out CO2. The CO2 you breathe out is the food you ate. It comes right from the sugar. You took that candy bar and you're making it into a gas. That's what you're doing. Or you turn into fat. Then if you use up fat, you're losing weight, you're taking that fat, you're turning into CO2. So it really is, you're burning it off. You're burning it off. Just like when you burn paper, what do you produce when you burn something? CO2. So when you see Mr. Skinner or any of your gym teachers tell you you're burning off calories, you really are. You're taking that carbon that was in sugar, that got turned into pyruvate, and is now turned into CO2 gas. And then that CO2 gas in a plant either goes back into the chloroplast or leaves, and usually it's just used up in the chloroplast. Does that make sense? That's why the net gas that leaves the plant is oxygen, because almost all the CO2 keeps getting used up and you make it back into sugar. But it does put out some CO2, right? Some CO2 comes out, just mostly it's oxygen. Then you have a bunch of electron carriers, which again we'll talk about, we'll look into them. They're different electron carriers. They're called NADH. What's the difference between this one and the chloroplast one? There's no P. So NADH and FADH2. And that's just 2 electron carriers. I'm going to have you know them. I'm going to ask you to know them because they're pretty well known. Why not know them? A lot of this stuff we can get into, and we could spend a month on this alone, but we're not going to. All right. So these are just electron carriers. By the way, this also, glycolysis also produce something else. Some NADH and FADH2. And what do you think is going to happen with these electrons? They're electron carriers, right? What are they going to do with them? They're going to do what?
Transport electrons.
They're going to transport electrons to where? Where are you going to transport these electrons? Where do these electrons all go? Into the mitochondria, but where do they go in photosynthesis? What do we do with these electrons from the light reactions in photosynthesis? They went into the Calvin cycle. Where in the Calvin cycle? No, they came from photosystem 2. These electron carriers got charged up in the electron transport chain. So these transporters took them to the electron transport chain. And eventually, you're right, they took them to the Calvin cycle where they were used to reduce one of the components. But it turns out that this goes to the electron transport chain. And when they go to the electron transport chain, you're going to take the oxygen, which is also coming from where? Where's the oxygen coming from? Photosynthesis or the atmosphere if it's a human, right? Because we don't do photosynthesis. It's going to take the oxygen. First, it's going to take the electrons and it's going to run ATP synthase, and what's it going to do? Create a hydrogen ion concentration, right? It's going to use the electrons to do what? What did we do in the electron transport chain in photosynthesis? What was it? What were all the electrons for? For creating what? A hydrogen ion. That was on your quiz, wasn't it? Hydrogen ion concentration. That's right. Gradient. And of course I messed up because I'm thinking, So you create a high and a low, right? Why do you create a high and a low? So you can create a what? So you make a tunnel, right? And what's going to happen with the tunnel? What's it going to do? Hydrogen ions are going to do what? That's right. And so what's going to happen is ADP plus phosphate will turn into ATP, and it's going to do a lot of it. And in fact, it produces a ton of ATP now. And so now you get, this is what's going to make your most of your ATP. In the cell is made in the mitochondria. Sure, you make a little bit of it here, you make a little bit of it here in the Calvin cycle, but the majority of the ATP is made by the electron transport chain in the mitochondria. A lot of it. And where did that energy where did it start? It started with sunlight. If we did this summary reaction, it would be C6H12O6 plus and this, it depends on which way you go, right? So we could take sugar, C6H12O6, add it to, oh, by the way, the other thing, what do we do? The oxygen ends up being the last electron acceptor, and then it takes the electrons and makes what? What do you think it makes? Oxygen takes the electrons, there's hydrogen around, there's oxygen, there's electrons, makes water. Makes water. You make water every day in every cell of your body. You're making water if you're using sugar. When you eat sugar, that's why, by the way, a lot of doctors tell you if you're overeating, it might be you're not drinking enough water. Because when you're not drinking enough water, what does your body want? Sugar. It wants water, but if you're not drinking the water, what's it going to call for? Sugar. Why? Because what is sugar going to do when you break it down? Turn into what? Water. So you're making water when you break down sugar. It'll take the oxygen from the air and make water in your cells. So if you don't give it enough water, your body's going to say, I'm hungry. There's another good reason to drink more water. Yeah.
So only glucose does this?
Glucose is it's a good point. There are other ways that fats will also jump in here, but ultimately a fat won't has a lot of energy, but it comes in and gets turned into a different component. I don't want to get into it, but it does come in and it does feed into the system. All right, but ultimately oxygen comes in and turns into also proteins. Will do this as well. So you can break these things down. Your body has all kinds of ways to change them into what's called intermediates. And those intermediates can jump into this chain of chemical reactions and give you energy. But glucose is the main molecule. It's the daddy of all sugar, all chemical molecules, right? So here's the water it's made. The water here is going to go where? Back to photosynthesis.
Oh.
So it goes back, oxygen breaks, so that oxygen gets made into water, water goes back in. And even if we had plants and animals, as you have an animal that's producing water and taking up oxygen, well, you have a plant that's doing what? Taking up carbon dioxide that the animal's putting out and producing excess oxygen so that the animal can breathe. And so that's a relationship that we are endangering by tearing down our forests and making our lands not suitable for plant growth. Yeah.
So like after the water is made in the mitochondria, and then it goes back to the chloroplast break it up again.
That's right.
Hydrogen.
That's yeah. Everything's a cycle. That's how do we get life to exist on a planet for 3 billion years? We're not constantly getting more carbon coming in. We're not constantly getting more water coming in. We got the water we started with. That's what we got. Why haven't we lost it? If we're drinking it all the time, and if you can think of 1 billion people, 9 billion people drinking it all the time for all of history, plus dinosaurs, cats, dogs, all these things drinking water, why haven't we run out of water? Because we just keep cycling it, recycling it over and over again. In over 1 billion years, we haven't run out of, and as long as the sun shines and water's liquid, life can go on. Right? There's all kinds of other parts and pieces that are needed, but the bottom line is that that's why a cycle, why we recycle, right? That's why there's this big push for recycling, because you get sustainability from that. You can sustain a system long term. It can keep going, no problem. All right, so that's kind of a summary of where we're going with cellular respiration. But we should finish photosynthesis. And we got a few minutes left, about 6 minutes left, so I think that's enough to talk about the alternative pathways. There are these things called C4, 2 pathways, C4 photosynthesis, and there's another thing called CAM photosynthesis. Has anybody read that yet in the reading? What did you read about CAM photosynthesis?
CAM photosynthesis is used for plants in like extreme weather.
That's right. That's right. So when you're talking about alternative photosynthesis, you have to consider some interesting issues. So plants can't move, is that right?
Yes.
All right. So here's a problem. You have a plant that's sitting and growing, has a stem. On that stem is a leaf, right? That leaf is taking up carbon dioxide and it's putting out it's putting out some oxygen gas and taking in CO2. And it's going to do all this stuff that we just talked about. Now here's the problem. Rubisco is an ancient enzyme. It was around before there was oxygen, a lot of oxygen. So Rubisco was evolved when oxygen was not plentiful, or oxygen gas. So when there's a lot of oxygen, Rubisco would rather bind to oxygen instead of CO2. And that's a problem. Why is that a problem? If Rubisco fixes oxygen instead of CO2, what's the problem?
It's less oxygen in the air.
Well, let's remember, what is Rubisco doing? Think about what Calvin cycle is doing. Well, there's less oxygen in the air, but that's not really the problem. The problem is, why is CO2 necessary? Why was Rubisco so important? It's fixing CO2, what's it going to do? It's not really creating ATP, what's it creating? Sugar. It's the carbon in the carbon dioxide that's important, right? So if this Rubisco chooses oxygen instead of CO2, what issue do you see? Can you make sugar with oxygen?
No.
No, what do you need? Well, you need oxygen, but what else do you need? Carbon and hydrogen. We have hydrogen and oxygen, that's fine, but there's no carbon. So you need CO2. So if Rubisco chooses oxygen instead of CO2, then you get something called photorespiration. And photorespiration is no good. That leads to no sugar. No sugar means the system ceases to work. So plants have evolved to deal with this. All right, plants have evolved to deal with this. And what they've done to deal with it is they've come up with two different ways of handling it, depending on what the reason is. All right. There's CAM, and it's in your workbook as well as the chapter. There's C4 photosynthesis, and there's CAM photosynthesis. You need to know a little bit more about plant anatomy, actually leaf anatomy. On the bottom of leaves, there are these things, and this is where it's going to be kind of tricky. And this is one of those. We said the stroma. What's a stroma? The outside of the thylakoid in the chloroplast. But there's another thing called the stoma. So this is going to be the stoma. And there's hundreds of these stomas in the bottom of the leaf. And they're really creepy. They're two guard cells that guard the opening of a cell. And my drawing does not do it justice, so I'm going to flip over. I'm going to find you a picture of it. It's going to be freaky. It might give you nightmares, I apologize. They freak me out. That's all I can tell you. Like I eat leaves. I eat salad. I love salad. So the thought that this is what I'm eating freaks me out. So that's the opening. That's the opening on the bottom of every leaf, right? Is these guard cells surround an opening. Of course, that makes sense. You don't want just anything coming in and out of your leaf, right? If you're a plant, you want to be able to open and close it. They literally have thousands of these little mouths on the bottom of the leaves. It's just, it really is like, oh, are you kidding? They open and close on the bottom of every leaf. You can see it here. It's actually a stomata, right? Stomata. So we're pretty much done for today. We'll finish this on Monday. Make sure you're doing your reading because we don't have any time to prepare you more than what we've already talked about so read that chapter and do your workbook.